Okay. All right. So how has it been? I hope it's been nice. So we are going to start by, I'm going to start by asking if there's any questions from the previous lesson. Last lesson we talked about uh, embedded systems. So I don't know if there is any question from the previous lesson. If you have any questions from the previous lesson, can I see your hand? Okay. All right. So I guess there is no question from the previous lesson. We all understood uh what our tutor taught us last time. Okay. So there you said your deal was very stressful. Mine too, mine too, mine too. That's stressful. I don't know. Anyway, it's okay. All right. So today we're going to look at something different from what we did the last time. Today we'll be looking at processors and what it's all about, what it entails. So the question is, have we heard of processor? Have we heard of processor before? If you've heard of processor before, just drop me a thumbs up on the chat, chat menu. I'm going through that now. If you've heard of processor before, just give me a thumbs up. Okay, so it means you've not heard of processors. Okay. So have you heard of something, your laptop, you own a laptop and then they say your laptop is of an Intel processor or AMD processor. Have you heard of something like that? So that's what we are going to, that's what we're going to look at today. We're going to look at processors we're going to look at processors in today's class. So our trainer who is unavoidably absent today because he has some other things to do. So I'll be standing in for him. And if you have questions in the course of today's class, please just drop it on the chat menu, and then I will call you up, or I'll call you up to ask your question. And then this week, this month, what we'll be looking at microcontroller architecture, okay, which is the very core base. We do the very core basis of IoT. And then after that, we'll look at ESPs. ESPs are just basically Wi-Fi modules or Wi-Fi microcontrollers. Because the reason I call them microcontrollers is because they have an onboard SoC, that is system on chip, on them. So that's why I call them microcontroller. So we're looking at microcontrollers architecture. We'll look at ESP. We'll look at LoRaWAN, and we'll look at Raspberry Pi. Some of you must have heard of Raspberry Pi. So we're going to look at that this month. And then we'll look at different microcontrollers architecture, because those will help you know how you're going to program them and how to use them. And in today's class, once we're done with the general introductions of what is the architecture is all about, we'll pick up a particular microcontroller called the Arduino, and then see how we can do justice to that. So if you're good with me, can I just give me a thumbs up if you're good with me, so we can proceed to, I can proceed. If you're okay with me, just give me a thumbs up. Okay, okay, okay. All right, so let's proceed. Now, what really is a microprocessor? Okay, so a microprocessor is the heart of an embedded system. When you talk about the heart, you talk about main components that embedded systems run with. So it is basically the basic unit that takes input and then produce an output after processing the data from that very input. Say, for example, you have a sensor like a temperature sensor connected to it. The temperature sensor connected to it serves as an input to it. And then the value that the temperature sensor will be generating and then sending to the device to the processor is the data. What happens is that it's going to pick up that particular data, be it may be in voltage, maybe in resistance or whatever, depending on the type of temperature device sensor you're using. So it's going to pick up that particular data and then process that data. So with that, it's going to tell you, okay, with the process, with the values I've gotten, and then from the result of processing this particular data, so this is what is going to happen, and this is what is going to happen. So it is the basic unit that takes input and then produce an output after processing the data of that very input. So for an embedded system designer, it is very, very necessary for us to have this very knowledge of both the microprocessors and the microcontrollers. The microprocessors and the microcontrollers, they are different things. Okay, they are not the same, they're different things. So it's very, very needful for us to have an idea of what of this very, very device. So going forward, we need to understand what a processor is in a particular system. Basically, we have two types of processors have two essential units anyway, and these units are one, the control unit, and it also have the execution unit. So the control unit is basically the control unit basically fetch the information. Okay, it's used for fetching information or instruction from a particular memory. When you talk about memories of when you talk about memories, you talk about EEPROM or maybe the SRAM or as the case may be. So it's used in fetching memory or fetching instruction from that part from the memory. That's basically the control unit. And then the execution unit implements the instruction that pertains to the data transferred, pertains to data transfer operations and data conversion from one memory to another. So it's just like I've been able to get this, I've been able to fetch a data. So what is the information about this data? So what actions are around this particular data, or what are the instructions to be done with this particular data? So that's what the execution does. So the execution unit includes the arithmetic and logical unit, which helps in doing your mathematical calculations, your addition, your subtraction, your multiplications, as the case may be. It also carries your logical unit. Like when we talk about logic, we talk about AND gate, we talk about AND gate, we talk about OR gate, we talk about NOR gate, and we also talk about NOT gate. So it handles that part. It has that particular unit which has the whole calculations, the addition, the subtraction, and then the whole logic to know if it's good to work with or not really good to work with. Then it also has a circuit that executes instruction from a program control type, such as interrupt or jump to a particular system. So this interrupt basically is that you're doing a particular action, but you want to jump from a particular action to another one. That's where an interrupt comes in. So it's the execution unit helps you switch from a particular program, from a particular instruction to the next instruction. So for example, you're running a series of if statements. What do you need? You need an interrupt at that point to move from a particular statement block to the next statement block. Okay, so If my terminology is on the programming aspect of it is, if you don't understand it, please just drop me a chat on the chat bot menu, and then I'm going to respond to that. Okay. All right. So knowing that we have these two components inside this processor, now processors are divided into different parts. Okay. And then now these very different parts of processors are they're generally two. Number one, we have the general purpose processors, and then we have the application specific processors. Now, the general purpose processors are processors like the microprocessors itself, talking about the Intel, the AMD, the whatever processor series you're using, or then talking about microcontrollers, they're talking about maybe the 8051, or maybe what a PLC series. You're talking about maybe a AVR or Atmel or whatever series whatever series that you are using. Then we also have the embedded processors. These embedded processors are basically SoCs. Okay, these are basically SoCs, and some of them are used for some mathematical process or some mathematical calculation. So we have SoCs. Those are systems on chip. And then we also have digital signal processors. Those ones, digital signal processors and media processors, those ones are kind of used maybe in the video, or maybe in the media angle when you're looking at the graphics, as the case may be. So the application specific processors are basically these ones that are designed for a particular purpose. It's designed for a particular purpose. So that's the application specific system processor. So it can't really do lots of multitasking, like doing this one and doing that one, doing the next one at the same time. It's designed for maybe a particular like a specific purpose. That's what I mean by the application specific system processor. So in the course of the particular class, we're going to do talk more about that. So let's pick the first one, which is the processors, and then talk about the processors. So talking about processors are basically microprocessors are it's a single. When we talk about when I say VLSI, I'm talking about very large scale integration. Very large scale integration. Now, when you talk about manufacturing of different ICs, that's where the VLSI comes in. Very large scale integration. So now, microprocessor is a single very large scale integration chip having a CPU, that's a central processing unit. Now, in addition to this, it may also have other units such as the pouch, or maybe the floating point processing arithmetic unit, which helps in some addition and some subtraction. And then it also has a pipeline unit, which can also be known as the port, which can also be known as the port. Now, this helps in faster processing of instruction. Now, where you have different inputs and outputs, and this may be a timer, or maybe there's a signal at the serial communication at the serial communication at the port, and it needs to pick this signal. So with the help of all these combinations, it helps to work very faster. Now, the very early generation of microprocessors was only used a kind of fetch and execute cycle. This fetch and execute cycle was really a problem, and then processors couldn't work faster because of this very technique, where it has to fetch data, wait for a particular action to be done before it goes back to execute. So that one way communication wasn't really okay. So it needed the recent one, which is an Harvard architecture, by the way, which is an Harvard architecture, has separate memories which it can always talk to and then receive information from. Now, previously they had a clock speed of maybe from 1 megahertz to about 20 to about 2 gigahertz. Yeah, that's that's fast, but when we get to heavy processing, it really wasn't good, or really wasn't fast enough for heavy data processing. Now, talking about the block diagram of this. Now, looking at this, we have the CPU, which is which carries the central processing unit, and then we have the general purpose microprocessor, which is on board there, and then it has a RAM. Okay, it has a ROM. ROM are basically the memory. Okay, in which it serves its program, and then we have the RAM, in which it uses to process those particular programs served in its memory. Then we have the I/O ports. Now, these I/O ports are input and output ports. So the same port can be used as an input and can also be used as an output. All right. So let me just set an example of a port like the USB you have there on your laptop. Is both input and output. You can use it to send command to the laptop, and then you can also use it to send a command out of the laptop. Like, for example, when maybe you're using an external keyboard and then you're typing, you're sending in an input. Or maybe you are connected to an external camera, maybe a webcam, you're sending in an input. But when you are printing from the laptop, maybe you connect your printer to your laptop, at that point you're sending an output from the laptop to the printer. It also has a timer in which is used in running its sequence. And remember what I said, that it has a pipeline, okay, a pipeline unit which helps in running faster. So that comes with the serial port, where it does its serial communication. So that's just the block diagram for the microprocessor. Let's move to the microcontroller. Now, the microcontroller is also a single very large scale integration unit. Okay, it can also be called a microcomputer. I'm going to talk about why it can also be called a microcomputer. Now, although it have a limited computational capability compared to the microprocessor. Now, this possesses an enhanced input and output capabilities and a numbers of on-chip functionalities. When I talk about processes and enhancing input and output, like for example, the Arduino that we're going to talk about today, it has the ability to take a lot of input and output. You can have you can have lots of peripherals, external peripherals connected to it, and then it also enhances the capability, and then has a number of on-chip functionality that you can maybe use a certain communication protocol on it, or maybe program this, use it to run some other things. You can use to run another device. Okay, you can use to run another device, like you can use to run another machine, or you can use to run some sensors. You can use it for some communication. You can use it to develop a full project. Okay, so microcontrollers are particularly used in embedded systems. All right, now for real-time control applications with on-chip program memory and devices. Now, for example, which one can I say? For example, your air condition. Okay, recent air condition now has microcontrollers on board. Now, because with the ability of it to know to sense the temperature of the environment and then do an action based on that, based on the temperature of that particular environment. So this microcontroller, like other devices like maybe a refrigerator, or maybe your microwave. Yes, your microwave. So you put you put your meal in microwave, and then you set a timer. How does it know that it's the time it says, or it's 2 seconds, or it's 1 minute, or like 20 minutes? How does it know that? Or maybe your automatic doorbell. Okay, maybe if someone walks into it and then it recognizes that there's a presence of someone there, and then automatically rings people, okay, residents of that particular environment, that there's someone at the gate, or maybe your intercom. All right. So these are the few examples of what microcontrollers can be used. So let me use widely in a lot and lots of things. Or how about the street lights you have outside, street lights, to be able to detect that, okay, it's darkness, it's night, oh, let me turn on, it's night. Or maybe it's day, oh, day, let me turn on. Or maybe some other project like that. So there are a lot of functions, or a lot of programs, or a lot of devices that the microcontrollers are being used, okay, on. So now talking about the block diagram of a microcontroller, it also has a CPU, it has a RAM, it has a ROM, and then it has input and output ports, it has a timer, it also has a TIO port for communication. So we are going to talk about this. We're going to talk about the in-depthly when begin to talk about Arduino, because we're going to go in depth in picking. In the course of this training, we'll be making use of Arduino. The most when we start doing some programs, writing some programs, and then we'll show you how to write those programs to Arduino and how to run with Arduino. Okay. Now let's try to differentiate between the microprocessor and the microcontroller. So we can say that, okay, microprocessor, they are multitasking in nature, and they can perform multiple tasks, yeah, at a particular time. For example, on a particular computer, we can do music, or maybe we can, like what I'm doing now. I'm doing a presentation. I'm on Zoom, and then also my slide is on, so we can multitask or with a microprocessor. Or we can also be playing, if I want just to play music, and be playing music as well. So, but going over to a microcontroller, a microcontroller can't really perform this a lot of tasks per se. It's single task oriented. All right, it's single task oriented. So, for example, you have a particular device, for example, just your washing machine, and then it isn't just for the washing machine. So it checks if what time did I say to wash a particular material. Okay, to wash a particular material, I have to turn it for about maybe so RPM time, and then okay, yeah. So that's what basically what it's designed for. So it's single task oriented. All right. So it doesn't really do a lot of stuff. So going to microcontroller part, it has the RAM, it has the ROM, it has the port, it has timer, and it can add a external peripherals. Okay, it can also add external peripherals to can be added to it. But when it gets to the microprocessor, yes, it also has the RAM. The ROM has the IO input and output port. It also has timer, but it cannot really be added externally. Okay. Now these components have to be embedded together. Okay, on a particular chip. All right. So, like for example, your laptop, you have the RAM is just separate, and every other part is separate. So you can't really bring them together. Okay, but when it comes to a microcontroller, you can easily bring them together. So I'm going to show you a picture of an Arduino, and then I'm going to show you an architecture of Arduino where you have all of these things connected together. Then the designer can decide the number of IO ports it needs, but for the other one, it's fixed. It just has a fixed number of IO pins. So which it makes my microcontroller very ideal for limited tasks anyway. So it also has an external support for external memory, input parts, and everything. The microcontroller is kind of lightweight and cheaper than a processor. So the cost of acquiring Arduino Uno, I think it's about I think it's about $10 or so. Maybe if you convert that to naira, it's around 5,000 for 7,000 naira. The cost of acquiring a processor is far higher than that. So with this, we're going to talk about different architectures, and then we see how we can move further. So talking about architecture, what really is architecture? Architecture is basically how a computer hardware or software is being designed and organized. Okay, so now there are basically two types of architecture, and then some of them, one of them is not really in existence. Okay, one of them was used a long time ago, and then right now it's not really in existence. So so the first one is the von Neumann architecture, which was designed by John von Neumann. Okay, so it was designed by him, and then the next one is the Harvard architecture. So now the von Neumann architecture says that a particular a particular device, okay, is going to have just one memory. Okay, it has just one memory. So though it has a data bus and an address bus, but what happens? It doesn't fetch data from data or instruction from the memory simultaneously. Okay, so what it does is that it reads and writes, but it reads and then waits and then later on it writes. Okay, so it's just like when you're in school and then you're in a class and then the lecturer is dictating some notes to you. What you do is you hear and then you write. Okay, that's what the von Neumann architecture is all about. So it fetches the data, and then tries to do some try to process the data before writing the data back to the device. So now whenever we do try to enhance the performance of any microcontroller, now we cannot get away from the fact that instruction can only be done one at a time. So this is with the von Neumann architecture. So we cannot get away from that very fact that instruction can only be done one at a time. So and this brings the process of sequential action. Okay, so you have to do this one, and then when you're done doing a particular task, before you go to the next one, So now both of these factors now hold back the competence of a CPU, of any CPU using von Neumann architecture. Now this is the common bottleneck when it comes to the von Neumann architecture. Okay, so you can do tasks simultaneously. So simultaneous tasks is not really it's not really there. So let's just look at the block diagram of where this von Neumann architecture. So you can't really do tasks simultaneously. Okay, so look at this. It has the program memory. Okay, which is the read-only memory. It has the variable, which is it has the RAM, and then it has the SRAM. Okay, now which is the static RAM. So now it has the address and it also has the control. All right. So what happens is that it sends it has a data, say, goes in first, and then gets an information, gets an instruction, and then it pulls fetch the data, and then pulls only like fetch, pull, and that's just what it just does. So it doesn't really doesn't do a task simultaneously. It just fetch the data and then later on pull that very data. So if you're doing a kind of detection, okay, if you're doing a detection with this kind of system, it will give you some issues. If you're doing a detection, for example, there's something I designed some time ago, being able to detect someone who climbs the staircase to my house, to be able to pick the person image, detect who the person is, and then send me the details so that I can know if I'm to attend to the person or not. So if I'm using such architecture, the von Neumann architecture, it will have to get the data, fetch the data, try to run the data. The time it will take for it to completely process the data and then send me the response. Maybe the person will be in my house and then I'll be like, I didn't. How did they come? How did they come in? So this was the bottleneck in that particular, when it comes to this particular architecture. Now coming over to the Harvard architecture. So the Harvard architecture makes it possible for the microcontroller to have separate memories. Okay, just look at this particular architecture here. It makes it possible for the microcontroller to have different memories. So it has the ability to read from to multitask. Okay, so it has the ability to do read from the two memories simultaneously. So while it's reading from this one, it can be writing from this one. While it's writing in this one, it can be reading from this one. So that's the advantage of the Harvard architecture microcontrollers. And Arduino, what we're going to talk about today, is designed based on this Harvard architecture. So you can look at it has the instruction decode, it has the program ROM, it has the register space, and has the data. And then look at, if I'm going to just take it back, try to compare, put this image in your mind, and then look at this. It has data, okay? It has this data here going in and out, and then it has an address and a control that is going to the register space, and also has an address and control that's going to the program read-only memory. So this is the main advantage of this is because of these certain characteristics. This having the ability to do this and this simultaneously. Okay, having the ability to read two different memories simultaneously is one of the great advantage of the Harvard architecture. Now going back to the previous one, which is the von Neumann. The von Neumann doesn't have that ability. Okay, so it only have the ability here. It only do one thing at a time. All right, it just here. All right, it just there. So it doesn't do much. Okay. So just like you send someone an errand, then you have to wait for the person to come back before you can to give you the instruction or the information from the errand you send the person. So for you to process and maybe send the person back again and all those back and forth. So that's just that's what the von Neumann and that's just the difference between the von Neumann and the Harvard architecture. So now let's try to do a comparison. Let's try to put them side by side and then see what this is all about. So the von Neumann has a single memory to be shared by both the code and the data. Okay, it just has one simple memory to share both the code, okay, and the data. It doesn't have multiple memories. Okay, just one. So but the Harvard has separate memories for the code and for the data. All right. So you're uploading a program to a particular memory, and then there's another memory that holds the data. For example, let me just pick a popular example with this Harvard architecture. So you have the Arduino. Okay, I don't know if you've used Arduino before. Can you just give me a thumbs up? Just if you've used an Arduino before, you've seen Arduino before. We're going to talk about it in this class. Can you give me a thumbs up? Okay, so Richard, you've seen have you seen it or you've used it before? So can you just drop me a chat? Have you seen it or you've used it before? So let me know if you've only seen it. Okay, you've used it before. All right, that's very good. So now in Arduino, you can upload a program to the Arduino, all right, and then you have some temperatures or sensors that are attached to it. So now those values, the values that are derived, okay, from those sensors are saved in the data memory, not in the code memory. The code memory is different. That is why if you don't work with EEPROM, okay, if you don't save those data in your EEPROM, the moment you turn off the Arduino and then you turn it back, you turn it back on, you're now fetching those data fresh. Okay, you're now trying to acquire those data fresh. Okay, so the program memory, okay, the program memory and the data memory are they're just different. So that's a different. So it has that, so it can pick from this one and then pick from this one and then work simultaneously without issues. Not using the von Neumann, which has just one memory. You have to pull and then wait for it. You have to push and then you have to push and then wait for some time and then fetch and other stuff. Anyway, so another thing we need to understand is that under the von Neumann, processors need to fetch code in a separate clock cycle and data in another clock cycle. Okay, so it uses something like a sinusoidal waveform. Okay, it is something like a sinusoidal waveform where the first cycle is for fetching the the very first cycle is used for fetching the data, and then the other cycle is used for pushing the data from the memory. So when I talk about sinusoidal, signal, I'm talking about a signal like this. Okay. Okay, this is a signal. This is what I mean by a kind of sinusoidal signal. All right. So, you know, if we should plot a graph, here, and then we say let's just pick it from there, this particular point, and then we know, okay, let's just say this is a zero reference, this is a zero level. You can understand that at one particular cycle, okay, 90 degrees or 90 degrees of the first cycle is for the positive side, and then another, 180 degrees of the first cycle is for the positive side, and then another 180 degrees of the next cycle is for the negative side. Then it goes back there. So it uses its first cycle just to fetch code from the separate code, which is in a separate clock cycle. Okay, well, that's what I mean by a clock cycle. And then this a total of 180 degrees. We say that, okay, it has met a complete cycle. All right. So this is a complete cycle. All right. This is a complete cycle. What we've just done here is a complete cycle. So having 180 degrees positive and then 180 degrees negative. So if you add the two of them together, it gives you a total of 360 degrees. So now in the very first cycle, it fetched the code, okay, from it fetched the code from a different clock cycle, and then in another, it kind of pushes the data. So now it needs two clock cycle in order for it to function effectively. But when it comes to the Harvard uses just a single clock cycle to do whatever it wants to do. Okay, so in a single clock cycle, it's able to fetch data from either from the code memory or from the program memory or from the data memory. So it doesn't wait for the next cycle. All right. So you know, time is of essence when it comes to IoT. All right. So it's not going to be a thing that maybe you design an IoT device and maybe to turn on your fan at home, and then you press a button to turn on the fan, and then you have to wait for the fan to turn on. Something will happen now, or maybe a protecting device that maybe maybe an IoT circuit breaker that needs to disengage or open the circuit if there is any surge. Okay, if there's any surge. So when you press a button and then maybe you're using a von Neumann architecture, it has to wait for the first cycle and the second cycle to be complete before it can make an action. But Harvard architecture just go straight. Just one cycle is enough to do the action and then give you the results you want. Now, for the von Neumann, because of this, it has a very high speed. Though, but it consumes a lot of time. All right, it consumes a lot of time. Though it has a very high speed, but it consumes a lot of time. Now, for the Harvard, it has a very low speed, but it's not time consuming, because the reason it's not time consuming is that it's able to perform two tasks simultaneously. All right, it's able to perform two actions simultaneously. So it can be slow. It can slow down because it needs to pick data from here. Depends on it depends on the size of the data, okay, and the size of the program. Okay, that can make it slow down a little. But outside that, it has no other issue. So the Neumann design is very simple, but the Harvard design is very complex anyway. So this is just a general overview of what a microcontroller architecture is all about. Okay, so now we are going to take a particular microcontroller. There are many microcontrollers out there. We're talking about when you talk about the Atmel, there are a lot of Atmel out there. Atmel microcontrollers. There are a lot of PICs PICs out there. There are a lot of PLCs out there. There are a lot of microcontrollers out there anyway. So we are just going to pick one and then go deeper into it so that we understand. We have a deeper concept of what it's all about. So now this brings us to what we will be using in our training for this beginners class. So this brings us to this very microcontroller called the Arduino. Okay, so this is a Arduino Uno. This is R3 version. All right, this is R3 version. The picture you see up here is the Arduino Uno, the R3 version. Please, if there is any question, or there's something you don't really understand, please. I'm looking at the chat right now. So if you have any questions, just drop your question there, and then I'll pause and then answer your question before coming back, so I don't completely lose you. All right. Okay. So if you're okay with, if you don't have any questions from when we started from the beginning of microprocessor from processors to this very point, can you just give me a thumbs up? If you don't have any questions from there, but if you have a question, can you just give me a high five? If you have a question, just a high five. If you don't have a question, just give me a thumbs up so I know that we are all together. Okay. Edidion says there is no question. Any other person? Okay, I've seen okay, Richard Abby said no question. All right, so I can proceed. So now this is, like I said, this is Arduino R3, Arduino Uno R3. Okay, so what really is this Arduino? All right, what really is this Arduino? Arduino is just basically a microcontroller. It's a prototyping kit anyway. When I say that it's a prototyping kit, you can use it for maybe some test run of some of your projects. You just want to do just a simple test run. You can just pick up and and then solve that. It is very easy to use. It's not as complex as other microcontrollers in which you need you need a bootloader, you need something to burn the program into, and then some different IDEs in which you need a compiler and editor in order to sum your program together and then send it. It is not as complex as other microcontrollers. It's very, very simple and easy to use. All right. So a lot of students and hobbies use this Arduino a lot because of its simplicity. So it's very cheap anyway. And by the way, it's open source. So you can make any modifications to it. You can make any modifications to it to suit your own requirements, or you can add, you can subtract based on what you want. Okay, it's open source. So it's left for you. You can use it as it is, or you can make some modifications towards it. There are different, there are other types of Arduino out there, so we're not going to deal much, we're not going to dive deep into that for now. So it's also used a software, and also use API which can be used to call some functions or some programs anywhere from maybe a third party cloud or whatever. So the board layout, like I said, it's open source. So when I mean open source, you can modify it, or you can add anything you want to add to it, or whatever you want. You can just do anything you want to do with it. It's open source. There's the licensing is under it's open source, so there's room for modifications and anything. So now looking at this particular device, okay, the Arduino. Here is this is the microcontroller. This is the microcontroller. And this one is is called the Atmega. This is just the Atmega 328. Okay, this 328 P series. All right. So this is the Atmega, and then this other one. Okay. This one is just this other this also microcontroller anyway. But what this one does, that it helps you write program to this Atmel. So whenever you connect your USB to this, you can easily do a serial just for the serial port anyway. That's just basically what that does. So it has a whole lot of pins in which we are going to talk about. It has the crystal oscillator, and this is for power, this is for reset, and these are the GPIO pins. We talked about GPIO pins, and these are the GPIO pins, and these are for the onboard power. Like you want to get power, from it to another component, you can choose from here. Or these are all the analog pins. Now, the difference between these other GPIO pins, which I'm going to talk about it separately, is that these ones are for digital. Okay, these ones are digital pins. All right, from here down here, these ones are digital pins. All right, while here are analog pins. All right, when I talk about analog pins, we are talking about non-discrete values. Okay, we are talking about non-discrete values. So non-discrete values, we are talking about continuous varying values. Okay, those are the analog. Like for example, alternating sinusoidal waveform is analog waveform. All right, and then maybe you're getting a reading from a temperature sensor. It can be analog, although there are some temperature sensors that are digital. But if you want to use any temperature sensor, I'll prefer you use an analog temperature sensor, because it's going to help you get an accurate reading. Okay. Now, if you're using a digital the one that gives you a digital output, it uses something like an op amp to do the conversion, conversion. So that really won't give you what you really want. But if you use an analog one, it will give you essentially what you need to work with. Okay. So going forward, we have what this board is all about. Okay, let's just talk about the different components of this very board. So I said, like I said, that it's one of the most popular Arduinos available. Okay, which is the Arduino Uno R3. So now this very one now, which is Arduino, there are different types of Arduino. Like we have the Arduino Uno. I mean, like Arduino Uno, we have Arduino Mega, we have Arduino Lily, we have Arduino Nano, we have Arduino Mini, we have Arduino Micro. There are different Arduino out there. Okay, there are Arduinos for robotics. Okay, there are Arduinos for robotics, which gives you access, which it has onboard stable drivers, so you don't need to have an external. Maybe you don't need to put up an execution. You don't have any issues with that. All right. So now this very one is based on Atmel 328 microcontroller. It has 14. When I talk about 14 GPIO, it has 14 GPIO pins. Okay, from here to here the pins, and also this other one. So these pins can be used for inputs and also for these pins here can be used for input and also for output. That's why I call it GPIO pins. Okay, it can be used for input and can also be used for output. Now going back to this other slide, okay, this is more clearer. So you see, it starts from 0 down to 13. So from here to here, from 0 to 13 makes it 14. From 0 to 13 makes it 14 GPIO pins. From here to here, yes, makes it 14 GPIO pins. Now, these RX and TX can also be used for input and output, okay? But most times they're used for serial communications anyway. You're sending data from Arduino to another, maybe another microcontroller or maybe another microprocessor. You can use that TX and RX. So just for it can be used for serial communication. But aside that, it can also be used for it's also a GPIO. You can send in data out. You can send data out of it. You can receive data out of it. So now, like I said, it has that, and then it has USB connector, and then it has 16 megahertz crystal oscillator. Now, this 16 megahertz crystal oscillator, which is here, makes it possible that this particular microcontroller can run very, very fast. And then a quick and just a simple analogy I would give is that this device, because of this crystal oscillator, can run your program 16 million times in a second. How fast is that? I'm not sure you can calculate that fast, okay, to run a whole lot of the process 16 million times in a particular second. So in 1 second, it's able to run your data or processes 16 million times. So how is that? Can anybody attempt that? I'm not really sure anyone can really attempt that anyway. So that's for it, and then it has a reset pin. Now this reset pin is if you have you're running a particular program and then you want to interrupt your program, you just want to pause your program somewhere and then start maybe start afresh, okay? Maybe you were doing some actions and then you just want to pause the action somewhere and then start the action again. That's where the reset button, comes in. Though it has a reset pin here, now you can also do a kind of electronic reset, okay? Maybe you just want to reset it electronically. Yeah, you can work with this particular pin to reset it electronically. Okay, so this is the reset button, and this reset button is connected to this. So the only way you can do is going to use this reset button is just to pull the data to ground. Okay, just have pull down resistor and then just put the data to ground, and then it will reset this particular Arduino. Then after that we have the USB. Now this USB is used for writing programs into the Arduino. It's used for writing programs into the Arduino. Like for example, it has its own IDE, in which we are going to talk about it later on. Arduino has an Arduino IDE, so where you do your programming, where you do your typing, where you write your code. It's not only Arduino IDE you can use in writing code to Arduino. You can use maybe VS Code, or you can use CodeBlock to write programs into Arduino. They have some plugins or extensions that can access Arduino. So this is where you write your data. This is where you write your program into. I talked about the crystal oscillator. Now this very component here is the voltage regulator. Now the Arduino takes just 5 volts, okay? But this power jack here, with this power jack, you can give it up to 12 volts DC, okay? Not AC, please, it is DC. You can only take DC, not AC. So the maximum you can put at this point, you can give it a 12 volts, And then because of this voltage regulator, to regulate this voltage you're giving here to the voltage that the Arduino will be able to run with. So it will regulate this voltage to 5 volts, which is the voltage the Arduino is going to run with. Then we have other voltage, output voltage, like maybe you want to connect it to another component. So you're going to connect another other component to it, like for example, motion sensor, or maybe an ultrasonic sensor. Okay, so you can use the 5-volt pin, or you can use the 3.3 volt pin. I think one of the components that basically use 3.3 volt is NRF. NRF is a transceiver, or NRF use 3.3 volts, and also ESP. ESP is also used 3.3 volts. We are going to talk more about that later on. So every other peripheral that doesn't use 3.3 volts, you can send them. So you can send 5 volts to it. And then it has 2 ground, which is which you can use that to connect your peripherals. I'll talk about peripherals. I'm talking about other modules or other sensors to it. Then this voltage in pin is, if you don't want to send voltage through, if you don't want to power it through here, you don't want to power it through here. What I mean by that, I'm talking about you don't want to power it through the USB. You also want to power it through the the barrel jack. You can use a voltage in this voltage in pin to send 5 volts. Please do not exit 5 volts at this point. If you exit 5 volts at this point, you're going to damage the Arduino. All right. Do not exit 5 volts at this particular pin. If you exit 5 volts at this particular pin, you are going to damage your Arduino. So you're sending 5 volts here. So now these other pins are the analog pins from A0 to A5. They are basically analog pins used to send in analog signals into the Arduino. Now sending it analog signals into the Arduino. Now you also have, inside of it, there's something called an ADC. Okay, so when one is sending analog signal, it goes through an ADC, which is analog to digital converter. All right, so that analog to digital converter is going to convert that analog signal that you just sent, okay, to a signal that the Arduino is going to read with the digital, and then send it to the main microcontroller, and then the processing is done. So this is the main microcontroller, and here is the in-circuit serial programmer. Now the in-circuit serial programmer is that if you don't want to send your program, you don't want to send input through this USB port, you can send in code using this in-circuit serial programmer. All right, this in-circuit serial programmer is also linked with the RX and the TX up here. So you can send in code here if you want. And then this other pin here is for this. There's an LED here which is to indicate if there is power, if your Arduino is being powered up. So if it's powered up, it's going to this LED light, and it's going to come up. And then if you're transmitting and receiving, you have the LED for transmitting and then receiving down here. And then these other ones are for serial communication. You can use it for serial communication, RX, TX. Like you're using, you're having 2 different microcontrollers. You want to send signal from this particular microcontroller to another microcontroller. You can use this. And then you have the digital pins. Now these digital pins are not can be used. Can also be used as analog pins also. Now the reason I said that, looking at this, you can see something like a sinusoidal wave symbol, sign at pin number 3, pin number 5, pin number 6, pin number 9, pin number 10, and pin number 11. Now this means that those pins are called the PWM pin. That is the pulse width modulation. So anything that wants to do, anything that that has to do with analog signal, you can do it with that particular pin. Every other pin are used for just purely digital communication, input and output, ones and zeros. But for those pins that you have that sign, that sinusoidal sign attached to it are the PWM pins, you can do any analog. You can use it for any analog input and output design or communications anyway. So now, so this is just basically just a brief description or introduction about this particular microcontroller. So the next is the next is the architecture. So inside this very microcontroller, okay, inside this very microcontroller, this is what you have inside of it. Are you with me? Okay, I've seen a message here from Ididium. Ididium is asking, what is the Arduino used for? Okay, Arduino is a microcontroller. It can be used for a lot of things. Okay, so let me to just hold on for a bit in at this point. Now, the choice of your microcontroller is based on what you want to use for. Okay. Now this Arduino Uno is just it's 8-bit. So if you want to do computation which are higher than 8-bit, you can do it with this Arduino. We can do it with this very microcontroller. Okay. So Arduino is the microcontroller. It can be used for a lot of things. Okay. For example, your traffic light, you can use Arduino to design a traffic light. You can use Arduino in your washing machine. You can use Arduino to make a washing machine. You can use Arduino to design a whole lot of things. All right, a whole lot of things. Street lighting, traffic lights, or what again? Timers. Going to accelerators. When you talk about accelerators, you talk about devices that does an action. Okay, when there's an input somewhere. For example, you can ask it to monitor if someone is moving closer to your compound, or you can do a lot of things. You can do a lot of things with Arduino. A whole lot of things. All right. So now in the project today, when we go deeper in this particular lesson, we are going to be picking out different projects in which we deal with Arduino. Okay. So now we just beginners. Okay. So we're just trying to understand the concept of it. When once we start doing projects, we're going to see different projects in which we can do we did. But if okay, if you have a question, please can you drop it drop it in the chat? I'll get your question there and then I'll answer you. All right. So let's if okay, I've answered your question. All right. So now, like I said, inside the Arduino, okay, this Atmega 328 is this architecture. All right, is this architecture. Remember I said that it's the 8-bit microcontroller. Remember I said it's an 8-bit microcontroller. So there are some computation that you can't really do with that. I think there was a time I was designing a project, and then I wanted to do what was the name of the project? Okay, I wanted to do an IoT board. Okay, like I can send information. Okay, and then it will display on any screen I want to display anywhere. So I was using Arduino to design this, and I was just relying on text alone. So that was when I started programming newly. And anytime I try to put text strings that are like more than 8 bits, it will cut off the first part and then we'll just print the other part. Then I was kind of wondering why I was having that issue. I checked my programs and then I asked mentors about it, and then it was a particular mentor that told me, oh, the Arduino you're using is limited to 8 bits, so you can't do anything more than 8 bits. So there's no way you can get higher text, higher characters more than that. So I had to switch from Arduino to another microcontroller, which was able to handle more than 8 bits. So that's how I was able to overcome that particular challenge. So it has a bidirectional addressing. Okay, it has the general purpose registers. It has the ALU, the arithmetic and logical unit. It has the data RAM. So you can see a memory here. You can see another memory here, and then you can see this is the first memory. You can see another memory here, and then where again you have a flash memory here. You have memories all through. So this Arduino is based on the Harvard architecture. Okay, this Arduino is based on the Harvard architecture. So it simultaneously picks pick data instructions from different parts wherever you want it to. So when you connect it to a particular component, or maybe you're using with a particular sensor, so what happens is that the data you generate from that particular sensor is saved in the data RAM. Okay, it's saved in the data RAM. So at any time you want it, you can always go. You can always fetch data from that particular data RAM and then run with that particular data. You can see the index in the indirect addressing. Okay, from the data RAM up to the program counter. Okay, then from the 32, it has 32 or 32 of it has 8x8 general purpose registers, 32 of them, of 8x8 general purpose registers. It has about 32 of them on board, and then it has an interrupt unit, it has an SPI unit, it has a watchdog timer, analog comparator. It has IO module 1, IO module 2, and then IO module N, and then IO line, and then a whole lot of stuff. It has the control line, it has the instruction decoder, and then it has the instruction register. So now, when you write, when you send program, okay, when you send program to it, it goes through the whole of these. Okay, your program goes through a whole of these before giving you getting an answer. So it goes through from this point to this other point to this other point before getting a particular answer for you. So you can see that it has about 3 timers there. It has about 3 timers and watchdog there. You can see it has internal and external interrupt, in which you can use to interrupt maybe whatever you want to do. It also has a UART that is connected there. It also has a UART that is connected there, and then there are a whole lot of it has a whole lot of things that is that's the UART that is connected there, and then it has two-wire interface, two-wire serial interface. It has the SPI, then it has a 6-channel 10-bit analog to digital converters. Okay. So now you can always have access to, so you don't have, you're not limited to anything you want to do with this. You are always, you can do anything you want to do with Arduino without any issues. So now, when we talk about this particular architecture, anyway, when we talk about this particular architecture, so now you can say that there are input and output registers there. And by the way, before it even gets to these registers, it starts with binary. It starts with binary. So we have the binary. It goes talks about the clocks. Talks about application flash section, and then the boot flash section. And then all of these it does all of these with the help of the decimal code. And then getting into the registers, okay, getting to this registers, which is here. Now, it stores the value of a particular memory. It stores the value of that particular memory in hexadecimal. Okay, for example, maybe I'm writing a variable. Okay, you know that variable is just you know what variable now is just a memory. Okay, in programming. Okay, so I'm writing a particular variable. So what happens? It's going to save the value of that variable I'm writing in the shift register. Okay, so it can have like the most significant, but it has the most significant bit, and then it has the least significant bit. So ranging from the least significant bit is a 0, and then the most significant bit is 7. That's why I'm talking about 8 by 8 general purpose registers. Okay. So now this 8 by 8 general purpose registers, they are all memories. Okay, inside when they're all memory module, they're all memories. You have maybe a 0, 1, 2. Since in binary, it is 0, 1, 0, 1, 0, 1. They're all in binary, 1 and 0, 1 and 0, 1 and 0. All right. So with the 1s and 0, 1 and 0 tells you, okay, that hey, this is a certain the certain number of memory size you use or whatever. So you can decide to use a whole lot. Can decide to use a whole lot because depending on the program, maybe you're declaring global variables or maybe local variables, a whole lot. So the memories, they're all there. It's all set in the registers. So for example, maybe you are doing something that takes a binary of maybe 100 and maybe 100 and 243. Okay. Now in hexadecimal, that is F3. Am I correct? In hexadecimal, that is F3. Now usually in programming, you're going to see something like this. Usually in programming, you're going to see something like this. Let me see if I can bring that up. Okay, you're going to see something like 0 and O X, and then F, then 3. Okay, this is how it's written in a. This is how it's written anyway inside that particular register. So if you have a binary of 1, 2, 4, 3, that is about about 1, 1, 1. That's about 4 1s and then 2 zeros and 2 zeros. Okay, I'm talking about 1, 1, 1, 1, 0, 0, 1, 1. Okay. By the way, this is binary. This is binary. Okay. Don't mind the way I'm writing. Okay. Just I'm using not with my pen. All right. So this is just the decimal value of this is 243. So in binary, you're going to have this. So if you want to write this in a restriction register, so it's going to take this particular format. Okay. It's going to take this particular format. Okay, it's going to take this particular format. All right. So and then that's how you write into that particular shift register. So now when you talk about these shift registers on an AVR, okay, an AVR, I'm talking about the ACML anyway, and ACML is an AVR. So the data register on the AVR is like the flash program memory, okay. Now they are organized as a continuous set of address, but with different specialized sections, okay. So they are organized as a continuous set of address, but with a different specialized sections. Okay, just like I said, let me see if I can just draw some of it. Yeah, let me can draw this here. So it has a section like this. Assuming don't mind my drawing. I hope it. Hope I'm able to get that up. And then this is MSB and LSB should be somewhere. So this is going to be like 0, 1. So that's going to be like 0, 1. We have 1 here. We have 0. We have 1. As the case may be, just it continues like that. Let me see. I think that we are talking about 8. And then we have another. We have another 1 here. Okay, we have another 1 here, and then it still continues. And then we have another 0, and then we have another 0, and then we have 1 at the end. Okay, we have 1 at the end. Okay, so please don't mind my drawing. Okay, it's because I'm just using a mouse pad. See, I can draw this up for you. Okay, so now here is the when I talk about the it's a continuous, when I say that they are organized, okay, as a continuous set of address with different specialized sections. So these are just the different specialized sections, and then here you can maybe have the hexadecimal value of maybe of the 0xF3, okay, which is for 243 of that particular maybe memory you want to save in. So now, unlike the flash memory, okay, now this different section refers to the physical this different section refers physically to completely different types of memory. Now, the largest set of registers refers to the RAM, okay, now which is a volatile memory for sorting data such as variables, strings to be outputted. Okay, so like I said, the largest set of registers refers to the RAM, okay, which is volatile. Okay, it's a volatile memory, and it is used for sorting data such as variables or string which are to be outputted. All right. I don't know if I'm losing anyone there. Please, if I'm losing you, please just drop your question. Just if I'm losing you, just drop your question so I can pick it up. All right. So now, going forward, now another set of registers are the general purpose registers. Okay, which are these which they are which are 32 of these. And now this I'm trying to put up, there are just 32 of them. And then the whole small amount of data which are directly acted on by the arithmetic and logical unit. Did you get that correct? Now, the whole small amount of data which is directly acted by the arithmetic and logical unit. So so when you're performing some calculations, some computation, so maybe for example, we are saying that if temperature A is greater than temperature B, or if temperature B is greater than or equal to temperature A, do this. Okay, that's the logic anyway. Or for example, we are saying if temperature A and temperature B equal to a certain value, do an action. So now this memory here holds that data. This memory here holds that particular data for the ALU to use in the computation. All right. Now, so now when the program gives an instruction to add two numbers, okay, like for example, you're writing a program that say maybe int A, int B, and you're saying that you're now saying that C is equal to A plus B, all right, which gives you a value. All right. Now, when the program is given, when you give the program an instruction, okay, to add two numbers, now this must be fed into the ALU from the working register. So it's going to be fed into this from these particular registers. Now, if the numbers are in the RAM, okay, if the numbers are in the RAM, what is going to happen is that they must first be moved to the ALU. All right. Now, this the other part is the other part that does the main thing is just a compiler. A compiler. If you have a very good compiler, now a very good compiler will make sure that that the transfer from RAM to the working register are minimized, because RAM access are generally they are kind of slow anyway. So remember we talked about the Harvard architecture. We said that it's a little bit slow, but it doesn't consume time. So now, if you have a good compiler, the transfer process from the ALU, from the register to the ALU, it can try to minimize that for you. But if you don't have a good compiler, it can be a little bit it can be funny a little bit. Anyway, so that's just a little of that. Please, our time is still on. Time is fast spent. I don't know if I can complete this architecture. This is very deep anyway. Now, talking about the input and the output registers. Okay, talking about the input and the output registers. All right. Now, the input and the output registers okay, they are used in order to read and write to the input and the output pins of the microcontrollers. Okay, the input and output registers are used, okay, to read and write to the input and output pins of the microcontroller. So when we're talking about Arduino, okay, when we're talking about the Arduino architecture, the Arduino architecture the other time, we now said that okay, we have can I bring that up? Yes, I'm talking about this pin, okay? Just basically talking about this pin, all right? I'm talking about that particular those pins. So now coming back here, so now the input and output registers, now they help you read from they help you read data from these read and write data to the input and output pins of the microcontroller. Now, but you really need to know, have a little knowledge of how basically the work, okay, how the input and the output data, how the information are being transferred anyway. So maybe we can do that in the next class because of time. You can do that in the next class because of time. So now the reasons for the input and the output pins are divided into like the reason they are divided into some the 8 pins is that this allows the state, okay, of the pin to be represented by 4 bits. Okay, we are going to talk about that in the next class. It tells the state of that particular pin to be represented by 4 bytes, rather it to be represented by 4 bytes. Now, each physical input and output pin corresponds to the logical bit on the port. All right. So the value of pin 3 on port D can give you can give you a value at some other point. There must be a corresponding logic value on that. Anyway, so there's something called the data direction register. Okay, so I don't know if okay, so let's just summarize from here so that we can pick it up in the next class. So we have port features also. We have port features which are all the which has to do with all the ports we're talking about. So the ports are basically the pins on a different port which also have different features. Okay. Some of those ports can be bidirectional. When I talk about bidirectional, it can be input, it can be an output. One of that particular ports is pin number 3, pin number 9, pin number 10, pin number 11. It can be used for analog input, can be also used for digital input. It can be used for an analog output, can be also used for both digital and analog input and output. Okay, in summary. Anyway, so that's just what I'm talking about, the port features. Anyway, so this helps you read data from some sensors, okay? Because in there's an ADC and DAC connected to it. What I mean by DAC, we're talking about digital to analog converters. And then once you send, for example, when you send a signal and then you want that particular signal to be in an analog form, and then maybe you're doing maybe you're trying to create an LED, and then you go through that. What happens is that it passes through a DAC, that is digital to analog converter. So it converts that digital signal to analog signal. So you can see your LED now beginning to brighten till it gets to the peak and then start decreasing, the lumen start decreasing till it also gets to the lowest till it goes off anyway. So that's just a brief explanation of this this computer architecture, this microcontroller architecture. So now, because of time, I'm going to pick up the other ones in the next class. Okay. So now let's look at the last stuff. They're talking about the architecture of it. We said that, okay, number one is the Harvard architecture, and then it because of that it has separate memories and buses, and just like in here, it has separate memories and buses. Having the separate memories and buses, just this is the bus I'm talking about. These are the bus I'm talking about. It has separate memories and buses. So with that, so it has the ability to pick program from one particular point memory to another. It's able to pick different programs anyway. So that's just one of the advantage of this particular microcontroller architecture. It runs on Harvard architecture. So now, the instruction executed is in single level pipeline, which has to do with ports. Okay. Now, instruction execution is in a single level pipeline, which has to do with the port. Then it also has a fast access register files, which are 32 by 8-bit general purpose registers, which is this other this one I'm talking about here. Okay. This very one I'm talking about in here. Where's my pen? Okay. Right. So it has the registers here, and then from there, talk about this registers here. All right, here. So because of that, it's able to process things it's able to assess. You do a kind of a computation and then on calculation. It's very fast to go to the register, pick it up, send it to the ALU, and then give you results in less than no time. Remember, I said that it can run 16 million times in a second, so it's very, very, very fast. Anyway, though, if you want to do when we get down to real time of autos, we're going to see why we say it's a little bit slow when we get to autos. Well, I'm going to tell you why we say it's a little bit slow. So it is a single clock cycle at a time. So it's not like the von Neumann that the first cycle, okay, the first cycle it has to do with some the first cycle has to do with some fetching, okay, and then the next cycle has to do with pushing, okay. It fetch and push, it fetch and push, it fetch and push. So it's not like that. So what I mean by this is this cycle. So it has this, and then in the cycle itself, so it's just one of these particular just one of these cycle. Okay, it doesn't use the two. So one cycle is enough for it to do whatever it wants to do. All right. So not like the von Neumann that uses both cycle. The first one to fetch, then the second cycle to push. But for this one cycle is enough for it to do whatever it wants to do, because all of them, all the memories are running simultaneously. All right. And also, since it has a single clock cycle access, the ALU will also run in single cycle operation. All right. The ALU runs in single cycle operation. So you don't have to wait for some things to happen before for some time before you're able to get your data maybe somewhere or somehow. So that is a summary for what we have for today. And then the reference for this particular class, I took the reference from these are all the sites I took the reference from. So don't worry, the slide is going to be made available on the channel. So if you want to go through the slide again, and then you can go through it again, and then you can also have it on the YouTube YouTube channel. You can also, I think this video is recorded there. So thank you so much for today. I'm going to pause here for questions. If there is any question based on what we've done today. We started on processors, trying to know what different processors are all about and what they can do, the different types of processors, the type, what they are being, the classifications, and everything. We also try to talk about architecture, the different type of architectures we have, and then which one is best and which one is not best. And then we also talked about we also narrowed down to Arduino, and then we said that Arduino is it's open source and it's what we're going to be using most of the program in our classes also. So we said that Arduino uses an Harvard architecture, and then it's very robust, and then can do a lot of things. All right. So I'm going to pause here for question. If you have any question for me, can you just drop it on the chat button, and then or you can just raise your hand and let me know. Do you have any question? Is there any question there for me? Just raise hand, and then I'll pick you up, or you drop it on the chat. And after this, next class, we'll be dealing extensively. We're picking ESP extensively to deal on. We'll be dealing on ESP extensively. So we'll go deep into ESP to know how we can use it, as IoT, how we can connect to your Wi-Fi, and we're going to do a lot of things with ESP next week. So don't miss the next class, because it's going to be very, very comprehensive. Okay, so in the absence of any question here, I want to say thank you for giving me your time today, and thank you so much for giving me your time today on this particular class. And then I'm going to see you again next week. So thank you so much, Abatifleke. Thank you, Daniel Escudo. Thank you, Edidion, Celestine, and Richard Fabio. Thank you so much for joining, for being with us today. So if you have any question, you can drop it on the channel, the Slack channel, and then I'll be there to respond the question. And please, the task that was sent, try and do your task. All right, the task that was sent, I'll try and do your task. So thank you so much, everyone, and have a wonderful evening.